Hi, welcome to the second of the AMS Colloquium lectures. We're very pleased to have Avi Wigderson here from the Institute for Advanced Study giving these lectures. He's an amazing mathematician and computer scientist who's contributed fundamental results to everything from trade-offs between hardness and randomness to zero-knowledge proofs and all sorts of other topics. And what he'll be telling us about today is proving algebraic identities. So please welcome Avi Wigderson.
Okay, thanks, Henry, and thanks for coming. I'm going to, in some sense, continue my talk from yesterday, but really starting from scratch almost completely and telling you about this very basic topic of proving algebraic identities, something that's a very basic part of math. So the plan of the talk, it will, it will go into, like yesterday, into several different areas. I'll introduce this problem of testing identities. And then in order to define it better or more formally, we'll need to talk about algebraic complexity theory. So there'll be like a 15-minute tutorial into this very wonderful field within computational complexity. And after that, I'll be able to define better testing algebraic identities via symbolic matrices that we discussed yesterday too. I'll talk about the non-commutative singularity problem of such matrices, and then I'll talk about what I described yesterday basically is given algorithm for this problem. And I'll say something about the analysis of this algorithm, what are the key ideas that go into the proof there. And in order for this, we need to go into two areas. One is non-commutative algebra, in particular the theory of free-skew fields. And the second is invariant theory. And I hope you'll at least get a sense of how these things combine and how similar structures occur in very different mathematical areas for different reasons, but nevertheless they are connected. So let me start, and here's a theorem that you all know. In fact, you probably give your students, or if you are students, you got it to prove at some point. We are working over some field. All the questions will be interesting for all fields, but later we may specialize them. We have a bunch of variables, and so we are working with polynomials over this field. And we are interested in identities like the famous Vandermonde identity, such that the determinant of what's called the Vandermonde matrix is the product of the differences of the variables. This is an identity of polynomials. And you might wonder, how did Vandermonde came up with this, and how did he prove it? And more generally, I give you such an identity, I claim it's an identity, or I believe it's an identity. How do you test it? How do you check whether it's true? At least convince yourself that it should be true. Of course, this question is, exists in abundance all over math, and there are many identities proved, many conjectured. And the basic thing I want you to remember is that when you have many variables, a multivariate polynomial with many variables, the obvious way to test it, to test if a polynomial is zero is very easy. You just check that all coefficients are zero. But if you expand this polynomial to check that all its coefficients are zero, you work exponential time, so you'll never finish. So this is not the way. We want a better way, a faster way. So the general problem we look at is, given a polynomial represented somehow, and we'll discuss this, is it identically zero? That's the basic question of testing identities. And we'll also discuss the question for rational functions, which generalizes this, will turn out to be interesting. And the word problem is another word, another name for testing identities. You just have an algebraic structure like polynomials, rational functions. Objects may have more than one representation, and the word problem asks whether two representations are the same object. Okay, so in order to formalize how we are given a polynomial, I want to talk about arithmetic complexity, how we represent polynomials. And here's an example. Here's a polynomial. It's a product of xi plus yi. And the obvious representation for it, the canonical representation, sum of monomials, is exponentially long. This would not be the way we want to receive it, again, because it's too large. And of course, the way I wrote it down initially, if I want to write its computation, initially not as a sum of products, but rather as product of sums, then it has a very compact representation, which we prefer and want to study which polynomials have compact representations. So this is a model that we will use to represent polynomials, a basic model. So we'll have some field and variables. And the basic way to compute it is by what's called a circuit. You start with the inputs, the variables, and you start with any constant in the field that you want. And you start adding and multiplying them up. Okay, so that's a circuit model, and the circuit size I denote by S. The smallest circuit that computes a polynomial. Often mathematicians prefer formulas to circuits. Let me just say that I'll talk about rational functions as well, and there'll be divisions in the circuits also, but let's forget about them now. We can look at formulas. The formulas are just, well, the circuit is really a tree. There's no branching. You have to compute everything. If you want to compute something twice, you have to really invest the effort to do it. It turns out that even though they are different, these two representations, they are not different enough for this talk. There's a theorem saying that they are roughly, up to almost polynomial factors, they are roughly the same. So we'll ignore the difference for this lecture. And we will be interested in those polynomials that have short representations, that have simple circuits or simple formulas. Simple, I mean short, small. Polynomial in size, let's say, in the number of variables. And I want to stress that I will only care about polynomials whose degree is roughly the number of variables, or polynomial in the number of variables. So these are the easy polynomials, and I want to talk about which polynomials are easy to compute, are easy to represent. And this brings us to variance theory and the question of VP versus VNP. So I just called the easy polynomial VP. It's just variance P. These are the same classes as P and NP, only specialized to polynomials as opposed to Boolean functions. So we will look at this question of VP versus VNP. And the question is basically, can we, which are the easy polynomials? Can we efficiently compute everything we care about? All the polynomials, that arise in mathematics, naturally. So here are all polynomials, just all polynomials. And here are the easy polynomials. We know some polynomials are easy to compute. I know the determinant, is easy. The Fourier transform is easy to compute. The elementary symmetric polynomials are easy to compute. Multiplying matrices is easy. These are all polynomials. But of course, not everything is easy to compute. There are polynomials, let's say random polynomials are hard to compute. Just take all monomials, give random coefficients, and it's very easy to see that it's not an easy polynomial. But that's sort of not fair. We don't expect random polynomials to be easy to compute, and random polynomials don't arise naturally. So Valiant was asking himself, what are the, when I say the polynomials we care about, what are the polynomials we care about? Which are the interesting polynomials? And amazingly, you can define that. At least he gave a definition of what are the interesting polynomials. He called them, well, we called them VNP. He gave them a different, so it's a Valiant analog of NP. This contains the interesting explicit polynomials, the polynomials that you really might care about. For example, essentially all polynomials that arise in algebraic enumeration problems are there. All the polynomials that arise in statistical physics, partition functions, so on, are there. And one polynomial we'll care about, I mentioned yesterday, is a permanent polynomial, we'll soon define, is also there. And so I'm not going to define for you V and P, but I'll define it sort of via its complete problem, which is a permanent. And I'll say in what sense it is complete. So we'll care about, in order to understand the VP and versus VNP question, we'll just care about the relation between the permanent and the determinant. And I'll explain in what sense and why this will be enough to sort of address this question of P and NP. So we are working in our field for get characteristics too. And think of, I'm going to define the polynomials, these polynomials, permanent and determinant. And think of X as a matrix of variables, n by n matrix of n squared variables. And here are these twins. Determinant everybody is familiar with. And the permanent is the same polynomial if you just ignore the signs. There are no signs. Okay, so it looks even simpler. And these polynomials have a lot in common. They are homogeneous, they are multilinear, they have degree n on the n squared variables. Coefficients are really simple. They really look sort of like twins, but they are about as twins as these Danny DeVito and Arnold Schwarzenegger. Determinant, is something we are familiar with and is easy to compute, and permanent, as I'll discuss, turns out to be difficult. And what Valiant proved is that they are complete polynomials. They capture whole complexity classes. The determinant captures the complexity class VP, in a sense I'll explain, and the permanent captures, in the same sense, the class VNP. They are in these classes, and they are the hardest in their classes. So first, let's talk about the determinant and explain this completeness, and then we'll turn to the permanent. So we've known for centuries, since Gauss, I mentioned yesterday, mathematicians were designing algorithms for millennia. And that's just one more example. We know that we can compute determinant for numeric matrix easily. We can write a circuit for the determinant. And the complexity is about n cubed for n by n matrix. It's a nice exercise. Obviously, Gaussian elimination uses division. So it's a nice exercise for you to see that one can do the same without division. There is a circuit just without division that computes determinant. So this is an easy polynomial. It's in the class VP. And what Valiant showed is that it's complete. It's the hardest polynomial in this class. And what it sort of explains, even before we talk about what it means, what it explains, to me at least, is why. I mean, of course, everybody here is a mathematician. You grow up learning mathematics from high school on. You keep seeing determinants come, here and there in every part of mathematics. And you might ask why. So to me, this is you see that there are all these famous mathematicians that have determinants called after them. So why is this? Why is determinant there? Because of this completeness. So what does completeness mean? Completeness means that if you have a small formula, anything that a mathematician will ever write down or describe, it can also be described as a symbolic determinant. You can always do that. It's no loss of generality. Every polynomial you come up with is a determinant. That's the reason. And moreover, the size is preserved by this transformation. So if you have a small arithmetic formula, you can translate it to a small symbolic determinant, just by an affine transformation. Even more precisely, if the formula size is S, then there is a symbolic matrix of variables and constants, so that the determinant of that matrix is your polynomial. And this is so beautiful and so simple that I'm going to show you the proof, okay? So I want to prove the completeness of the determinant. Again, here's the statement. If I have a small formula, it has a symbolic matrix that, whose determinant computes this polynomial. And this will be by induction. of course, it will be by induction. If we have a formula, it has a natural inductive structure. We might as well use it. And you look at the top gate in this formula, it's either addition or multiplication. So this formula is either the sum or the product of two subformulas. And inductively, we already have matrices computing them via determinant. So let's try to use it. Yeah, it's too large a room to ask questions to the audience. So the obvious, the easy one, I'm sure you see, will be product. So let's do it. We have a matrix for G. We have a matrix for H. We just fill up a bigger matrix. And the determinant of this new matrix is, of course, the product of the determinants, therefore the product of these two polynomials. So that was really easy. And then we come to addition, and I'm sure that if you tried it, it's not easy. It's not clear what to do with addition. If you have two matrices, you want a matrix with determinant. But, maybe after an hour, you'll figure it out. So here's the way Valiant did it. He said, let's strengthen the inductive assumption. Let's assume that the matrix we are building inductively is not an arbitrary matrix, but it has this structure. It has ones on the subdiagonal and then 0 below. Okay, let's just assume it, and inductively we'll build it like this. So we have the same for M, we have the same for G, and we have the same for H. So it's still true that the determinant of this new matrix is a product, but of course it's not quite inductively correct. But if we add this little one in the corner there, it stays fine. So actually, multiplication remains easy with this trick. Of course, we have to check the basis of the induction also, but that's very easy. If we want a variable, we can do it by this little matrix. So now how does it help doing addition? It's very simple, again. I'm doing it fast, but you can look at the slides later again. We look at the same matrix. We really look at the same matrix, and all we have to do is add one row and one column. Let's add this row and this column. I claim that now, with this adding this row and column, the determinant of this big matrix is the sum of the determinants of the two smaller matrices. How do you see it? You just expand by the first column. There are only two ones there, and I won't bother with the proof, but that's all you need to do. It's really, really simple. And the only problem is, again, we changed the inductive structure. We sort of introduced ones in the lower part, lower triangular part, but we can just switch this row, and everything magically works out. So even if you didn't follow everything here, it's a really simple proof that takes any formula into a symbolic matrix whose determinant computes as polynomial. And that's the completeness. That's why symbolic determinant represents every formula. Okay, so this was determinant. And now, if we want to ask whether VP equals VNP, this analogous question to P versus NP in the algebraic setting, we should ask ourselves whether the permanent also has a small formula, or if we are using the determinant, the completeness of the determinant, we want to ask whether permanent can be represented as a small determinant. So this is really the question. Can we take the variables of an n by n matrix and put it in a larger k by k matrix linearly, and in such a way that the determinant of the big matrix will be the permanent of the smaller one, and we want k to be small. Let's say polynomial is small in n. So this is the question we are asking ourselves, and let's see what is known about it. So again, I'm redefining the question. What we want is an affine map from n by n matrices to k by k matrices, a map L, let's say. And let's call it good if this composition gives you the permanent from the determinant. And let k of n be the smallest integer for which such a map exists. So that's what we want to find out. And in fact, this question was asked many, many years ago by Polya, who observed that, for 2 by 2 matrices, you don't even need to blow up the size. Right? The permanent of this little 2 by 2 matrices is a determinant if you switch and you negate one of the variables. But he also noticed that for 3, it doesn't work anymore. And it was natural, how small can you embed permanent indeterminate. And in fact, it's not clear that there is a finite way to do it. But there is a finite way because it follows from variance completeness results. Permanent has an exponential size formula, so there is an exponential size matrix for it. And what this completeness means is that if you prove that this number does not grow polynomially, then you have separated these two classes. You have solved this major problem of algebraic complexity. And people try to prove lower bounds on this number, and the best that exists is a quadratic lower number. But what we want is a super polynomial lower bound. So I want to say something about approaches to this, and because we'll talk about one, there are sort of just direct algebraic methods or rank methods, and in algebraic geometry, they are very popular, called flattenings. There is an approach that was introduced by Marmali and Sohoni that uses representation theory and algebraic geometry that's in, more sophisticated tools, and well, both of them right now don't give us what we want. And the third one that still didn't give us what we want is what I discussed yesterday, is this connection, this sort of very mysterious and amazing connection between proving polynomial identities and this very problem of separating VP and VNP. So I want to talk about that. And we are back to the tutorial of algebraic complexity ended, and we are back to proving polynomial identities. So I'm reminding you the problem from the first slide. We are given a polynomial. Now we know how it's represented. It doesn't really matter which representation you pick from the ones we discussed. It's represented as a formula or a circuit or symbolic determinant. That's your input. And what you are asked is whether this polynomial is identically zero. This problem, as I mentioned before, has a very simple probabilistic algorithm. Okay, if you have randomization, then this problem can be solved really easily. How do you do it? You just plug random inputs to your variables. So plug random inputs to your variables and then evaluate the polynomial. So that's why it's really important that you have a means to evaluate it. It's given as a formula or a circuit or a determinant. So you plug random, in fact, small integers will suffice. If the polynomial was identically zero, no matter what you plug it, you'll get zeros. If it's not identically zero, it's very easy to prove that with high probability, you will get a non-zero. Of course, the slide has a mistake in it. Well, the second one should be that if P is not identically zero, you will get zero with low probability. And so the question we are asking ourselves, finding a deterministic algorithm for identity testing, is a question about de-randomization. It's about removing the randomness from that algorithm, from this very simple algorithm. That's what we want to do. And as I said yesterday, it looks like, okay, it's some specific problem that computer scientists may be interested in, but as I explained yesterday, we understood how important it is when this result of Cabanets and Impagliazzo from 2001 appeared, and sort of was somewhat shocking. It says that this problem is absolutely key to solving VP versus VNP. If you have an efficient deterministic algorithm for this problem, for identity testing, then you can separate, then this will imply a separation of VP and VNP. Okay, and again, I want to stress what I stressed yesterday. It's sort of amazing that an algorithm for one problem proves that there is no algorithm for another problem. Let's say for the permanent, no efficient algorithm for the permanent. The proof, I'm not going to go into this, is not that difficult if you know the tools. You need the tools from pseudo-randomness and diagonalization and basically complexity theoretic stuff. And I'm not going to talk about it. I want to talk about, how do we prove polynomial, how do we test polynomial identities? Maybe that's the way, that's the right approach for the big problem. So again, this is a Cabanet-Impagliazzo theorem, and we want to find efficient deterministic algorithm for this polynomial identity testing. And it's hard. So what do you do when something is hard? There are basically three things I know about any problem that I encounter in mathematics that you can solve. Well, you either use assumptions, or you change the problem, or you weaken the problem. We'll see about that. So use assumptions. What kind of assumptions can you imagine using in order to develop this deterministic polynomial identity test? Well, you can look at the consequence. You can look at the consequence VP different than VNP. Will this make it? Right? We know it's a consequence, so we might ask about the converse. And in the same paper, Cabanes and Impagliazzo proved that this is indeed the case. So it turns out that if you have, if the two classes are, if permanent is harder than determinant, then there is an efficient deterministic algorithm. That's, again, a consequence of pseudo-randomness that I'm not going to explain. So with assumptions, we can do it. So it's sort of gives some confidence. Change the problem is what we'll do in the second half of the talk. So let me tell you just a little bit about attempts that are happening as we speak to find such an algorithm. And this is to look at weaker problems of the same nature. So what are weaker problems of the same nature? There's really a program that started with a paper of Dvir and Spilka. And the program is, just look at simple formulas and see whether you can test if they are identically zero. And just, build up techniques and hopefully lead to the main problem, to the general problem. So I want to give you a taste of how people do this kind of thing, or at least what are the tools that go into algorithms that compute identities, that test identities, at least simple identities. And I want to give you a flavor with this very, maybe the simplest identity that you can think of. And even this is quite non-trivial. So my claim is the following. A plus B plus C is 0, where each one of A, B, and C are just products of linear forms. I give you the linear forms, all, three sets of linear forms, and I ask you, is this identically 0 or not? It turns out that this is an efficient algorithm, and this efficient algorithm, okay, maybe I should say, why didn't I tell you just the sum of two products of linear forms? In this case, maybe this is the easiest case that's somewhat non-trivial, uses sum algebra. If you have just two products of linear forms and they are identically equal, because of unique factorization, it must be the same two sets of linear forms, and you can just match them. So that's an easy problem, but 3 is highly non-trivial. And what goes into it, this particular problem, is the following. It turns out that it must be the case. So you get structural theorems in mathematics, in algebra. In this case, you get that you can prove that the dimension of the set of linear forms, maybe there are many of them, maybe a polynomial in n, many linear forms, their dimension, total dimension, must be really small. If you use error-correcting codes, you get something logarithmic, and if you use what I'll show you, results from combinatorial geometry, you can even reduce it to a constant. So such an identity cannot live in high dimension. It must be somehow confined. And the way to see it is the following. I want to see what it means that this is A plus B plus C is identically 0. Imagine that we set one linear form, one of the A's to 0, and one of the B's to 0. Right? That makes the first two expressions. These are products. It must force C to be 0, so it must force one of the CJ's to be 0. In other words, you get some kind of a collinear triple. These 3 points, 3 linear forms are on a line. They have a linear relationship between them. And those of you who've seen this beautiful theorem will recognize how it's related. This is something that we don't quite get. We need more than that, but that's a famous geometric fact, the Sylvester-Galai theorem that's related to what I showed you. If you have a finite collection of points, doesn't matter in which dimension, in real space, and suppose I tell you that what we've seen before happens for every pair. Every pair of points you pass a line through must hit a third point. Suppose it has this condition. So You start drawing lines through pairs of points, and it always hits a third. This happens every time. Of course, this would happen if they were all on a line. In fact, that's the only possibility. That's the Sylvester-Galai theorem. And stronger theorems imply what we've seen before. So these kind of theorems give us good algorithms for polynomial identity tests in special cases. And now I want to move to the general case, to testing polynomial identities in general, namely testing identities, testing whether the determinant of a general symbolic matrix of linear forms is identically zero. Let me check my time. Okay, so this is the problem. We are given a matrix of linear forms, and like yesterday, one canonical, one really good representation of such a matrix is every one of the variables has a matrix coefficient. So x1, you put into the matrix A1 all the matrix coefficients of the variable x1, and so with x2, x3, and so on. So a way to represent a symbolic matrix is simply by a tuple of matrices in the field, one that for every variable. And we are given such a matrix, and what we are asking ourselves is whether the determinant of this matrix is identically zero. That's a symbolic determinant problem, and we call it the singularity problem. It's the same problem. We are just asking whether this matrix is singular in the field of rational functions, right? That's equivalent to the determinant being identically zero. And this is true if the variables commute. So until now, of course, you should have assumed that the variables commute. That was the original problem, and that's the problem we really want to solve. But unfortunately, as I said yesterday, we don't know how to solve it. That's a major open problem we want help with. And we are going to switch the problem. Changing the problem will be switching to the problem of trying to do it in the case of non-commuting variables. So in the commuting case, we are trying to invert a matrix over the field of rational functions. We said we don't know the complexity if we don't allow randomization. And when the variables do not commute, we are asking about the inversion of this matrix. And where are we inverting it? We are inverting it in the non-commutative field of rational functions, which I'll define for you soon. I didn't do it yesterday, so there'll be a meaning to this question. And as I mentioned yesterday, this seems like a harder problem. Even decidability of this problem is not obvious at all. It was proved by Krohn. Then with Rethenauer, they found an exponential time algorithm. And there it stood till about 2 years ago when we introduced these techniques that I'll explain. First for fields of characteristic zero, and then for fields for, in fact, arbitrary fields if they are large enough. So there are very different two algorithms for this problem of testing non-commutative singularity. So I have this acronym, NC-SING. This is non-commutative singularity problem of symbolic matrices. And I want to tell you about what goes into this algorithm. I described the algorithm yesterday. I'm not going to describe it again. I'm going to talk about the tools that go into, well, first the meaning of non-commutative singularity, and then the tools that are used in proving the bounds needed there. So there'll be just 2 slides on one of these topics, non-commutative algebra and invariant theory. These are the main sources of techniques and also where the applications are. Most people work with commutative, well, I don't know if most people, but anyway, things in the world don't always commute. The order of things matter. So I want to explain what is the field of non-commutative rational functions. And unlike the normal field of rational functions in commuting variables, it's a really bizarre object. If you never encountered it, well, I'll give you some hint of that. So we have some set of variables, they do not commute, and we are working over a normal commutative field. And polynomials, we still know what they are. We just write monomials. Of course, monomials now, the order of multiplication matters, but still defined by the coefficients. Now, when you localize it, you want a field. In the commutative case, you just take ratios of polynomials. It's very simple. Well, this you cannot do here. Rational functions, the only way that people represent them is just by a circuit or a formula or an expression. You just write down a sequence. You just write down a formula using plus, times, and inverse, or division. Right? So that's, you represent it computationally. That's how it was represented. So these are what rational functions in this free skew field are. And you already see with this very simple example, x inverse plus y inverse, that there is no way to write it as a ratio of polynomials. You can check. I mean, it requires some thought, but okay. So it's a more complicated object, and in fact, it gets worse. Look at this expression. In this expression, we have nested inversion. Right? In the commutative case, we can eliminate nested inversion. Here we cannot. In fact, it's as bad as this. There are expressions with arbitrarily high nested inversion that you cannot simplify, where this nested inversion is essential, like this. Two nested inversions here are essential. There's no simplification. But sometimes you can simplify. If you look at this very similar expression, here you can remove the nested inversion. It's not difficult to prove. It's called was identity because it's really the fundamental theorem of okay, I have to remember. So it's an important geometric fact, even though it's not clear from the statement. So sometimes two rational expressions, like with polynomials, represent the same object, but it's not evident, and so we are getting back to our proving identity now over this non-commutative field. I give you a rational expression defined, given by a formula. Is it identically zero? So that's a word problem for the free skew field, and that's what we are going to solve. In these two papers I mentioned, one for characteristic zero and one for general large fields. The first algorithm is analytic, the second is algebraic. Again, I'm not going to describe them in this talk, only what goes in, some of the ideas that go in. So let me start with the non-commutative algebra part. Here's what we want to do. We want to, again, check whether a rational expression vanishes identically. And the first result is the result of Kohn. The first key result that we need to use is the result of Kohn that shows that every rational expression can be embedded into a symbolic matrix inverse, into a question like non-commutative singularity. So, in other words, this is exactly the same type of theorem that I showed you, Valiant's theorem of the completeness of determinant, right? Determinant is whether a matrix is invertible in the commutative setting. I showed you that it can capture any polynomial identity. In fact, every rational identity in the commutative setting. So what Kohn proved is exactly the same theorem for non-commutative formulas. In fact, he also proved it earlier. But of course, this was done like continents apart, mathematically speaking. So this is what we'll use. And more specifically, let me just make it specific like I did with Valiant. If you have a rational expression, it can be converted to a tuple of matrices, to a symbolic matrix. Both the number of variables and the size of these matrices will be small, will be basically the size of the formula you are given. And this rational expression will be identically zero if and only if the symbolic matrix you get is non-commutatively singular. So this connects, this may be one way to define the non-commutative singularity problem. And there is even a stronger way to define it, and this calls for another fundamental theorem of Amitzur. saying that this expression is identically 0 if and only if the following holds. So you should imagine, I mean, if you have some expression in non-commutative variables and you want to know whether it's 0, you might start to plug in values. But what are values? These are non-commutative variables, so it makes sense to plug in matrices. What matrices? All matrices. All matrices of all orders. So that's exactly what's happening here. We are plugging for the variables matrices of all possible sizes, all possible matrices. And if every possible way you substitute the variables with such matrices vanishes, then your expression is identically 0. This is sort of natural to do, and Amitsur's theorem strengthens it really significantly. It says, I don't care about whether the resulting matrix, which is a huge matrix, vanishes identically. It's enough for me to take the determinant and see whether this determinant, this single number, is 0. If this number is 0, and this happens for all of these ways of filling up the variables with matrices, then it's 0. This is if and only if. This is a deep theorem, very important theorem. It will be used again, or its essence will be used again soon when we get to invariant theory. In any case, we have this set of equations that define non-commutative singularity. Now we have nothing non-commutative in this statement, so at least you understand what non-commutative singularity is. You can take it to be this definition. Another way to look at it, if you, instead of matrices di's, which are constant, you plug symbolic matrices of commuting determinants, just look at matrices of all possible sizes, and look at the determinant of this sum, then what you have here is a family, an infinite family, of commuting algebraic identities. So they are all 0 if and only if the initial matrix was non-commutatively singular. So we have a definition, and, well, does it help us? I mean, does it help us solve non-commutative singularity, this identity testing problem for non-commutative fields? Well, it would be nice if there was a finite number of things to test, right? So, for example, if we didn't have to look at all sizes of matrices, maybe there is some bound on the size D. And the key insight to the fact that there is such a bound comes from the fact that non-commutative singularity is a group invariant. If you change basis of this tuple of matrices from the left or from the right, some of you remember it from yesterday, if you change, this does not change the property of being non-commutatively singular. So since it's a group invariant, we better use invariant theory. And that's the last part of the talk. I want to give you, in 2 slides, the essence of what goes into these bounds and how they, well, maybe not how they affect the algorithm, but just how you get bounds on the number of, on the sizes of matrices you need to take in this expression. So try to remember this expression. It will come up in a couple of slides. So we're going to look at the invariant theory, the study of symmetries, and the group actions, orbits, and invariants. There are many examples. Those who came to Babai's lecture yesterday know about graph isomorphism. These 2 objects are the same if you apply the symmetric group on the names of the vertices. You can move from one to the other. You know, if you hit a ball and then let everything evolve, here the group acting is really just time, right? Once, you know, energy and the laws of physics will basically take care of the rest. And there is, again, an evolution or an orbit under the action of the group. Here, if you allow, you know, cutting and moving pieces about, you can transform one to the other. And so you have a group acting on various objects, and this group creates orbits. So there is a dynamics there. Things are changing, at least in appearance, but there are things that don't change, and these things that don't change are called invariants, and this is what you are trying to understand in invariant theory. For example, in the first, turns out that area is the only invariant. Any two polygonal shapes of the same area can be transformed by cutting and moving about the shape. It's the only and complete invariant. In the physical example, energy and momentum are the same, are the only two invariants. And in graph isomorphism, as you have seen from Babai, some of you, is really complicated. So the kind of actions, group actions we will look at are linear actions, actions of linear groups. So we have a vector space, and we have some matrix group acting on these entries of the matrix, and therefore they act on polynomials in this, if this is k variables, and if vectors of size k, then we have an action on polynomials with k variables. And what we are trying to understand, it turns out that all invariants are polynomial invariants. So we are looking for all polynomials so that the group action fixes. Okay, all polynomials P, so that if you apply the group to the variables, any group element to the variables, and look at what polynomial you get, it's the same polynomial. So this is called the invariant ring. And this is what the main objects of study that we care about today. And let me give you a couple of examples that you are very familiar with. First example is when the symmetric group acts on a vector by simply permuting the entries. Well, again, it's too large an audience to ask questions, but I'm sure you would have answered if I asked you, what are the invariant polynomials? Well, they are the symmetric, all symmetric polynomials. They are called symmetric because the action of the symmetric group doesn't change them. And moreover, this, this particular ring of invariants is generated by very few polynomials. It's generated as an algebra by the elementary symmetric polynomials, just n polynomials of degree up to n. So that's a really nice case where we fully understand what's going on. Here's another one where we fully understand. Suppose that we act on matrices, so now we have n squared variables. We act on matrices by changing bases on the left and on the right. Okay? So which polynomials in the entries of the matrix remain invariant under this basis change? Well, it's only that, they are all generated by the determinant. The determinant doesn't change, and all polynomials are just going to be powers of determinant. So these are extremely simple examples, and this is a kind of holy grail in linear invariant theory. You want to understand the invariant ring, you want to find small sets of generators for them of low degree, which are easy to understand and compute and so on. And the action we care about is actually a generalization of the second one, which I discussed yesterday. And this is, you don't act on one matrix, you act on a tuple of matrices, just a tuple of matrices defining a symbolic matrix. So the action is, again, you simultaneously change the basis either on the left or on the right. So that's how you act on a tuple of matrices. And the question is, what is going on here with the invariant ring? So let me tell you, and this is going to be the last slide. So this is what's called the left-right action. And again, here we have the tuple of matrices. We act on them by simply changing bases on the left and on the right. There are m times n squared variables. These are the entries of all these matrices. And again, the invariant ring are all polynomials that remain invariant under this action. And it turns out to be complicated to figure out what they are. It took many years. People were interested in this for various reasons. And the answer, amazingly, turns out to be the same set of equations we saw before, the determinant of the sum of the tensor products of the matrices with some arbitrary DIs of all sizes. So these are generators for all invariant polynomials under this action. So this same set of equations arises in a completely different area studied for a very different reason. And that's key for us because invariant theorists want to control the number, the degree of these polynomials, namely the sizes of these matrices. I'll just tell you what they did. I just want to say that understanding whether all polynomial invariants, which inputs, which tuples of matrices in this case, make all polynomial invariant zeros. It's called the null-count problem. I defined it yesterday also. And that's a basic problem of geometric invariant theory. And by the fact that you've seen the same set of equations before, this is another definition of the non-commutative singularity problem. So A is non-commutatively singular if all of these equations hold. So how do we, I'm not going to tell you what the algorithm that tests this is, but it definitely uses a bound on the degree, on D, on the size of the matrices that we need to plug in this expression. And this history is sort of amazing on this degree bounds. The first paper that dealt with it, this is 1890, the famous paper of Hilbert. In fact, this is the paper of Hilbert in which he proves the Null-Salazar theorem and the finite basis theorem. So all these amazing tools that build up commutative algebra were, he did it in order to get this result, a finite bound on the degree of any generators of invariant rings. And then people started improving it. There was double exponential upper bound, and then a very important result of Dirksen, given an exponential upper bound that was sufficient for the analytic algorithm that I mentioned yesterday. And finally, Dirksen and Markham, just very recently, sort of between these two results, proved the polynomial bound. And that led to the combinatorial algorithm that works over every field, takes non-commutative singularity over every field. I should mention that this result was proved using and sort of following what was done before in the previous paper and the connection to non-commutative algebra, and it uses this particular important result of Amitsur that I mentioned. So the connection between these fields is so now enriching them independently of algorithms. Okay, so to summarize, we talked about algebraic identities, word problems, and we talked about the completeness of symbolic determinant and symbolic inverse. We saw that the non-commutative case, this is solved, and it connects to many other fields of mathematics. The commutative singularity problem, this problem that's so connected to the VP versus VNP question, is still open. And it's a question of de-randomization. And one way to go about it, which I mentioned to some group theorists, is that we don't even know whether this variety that's defined by commutative symbolic determinant is a group invariant. I don't know. At any rate, there are new algorithms for invariant theory coming out of this work. I should say that this algorithm in P for testing the null-count problem is a rare example. I mean, in most cases, null-count problems, orbit closure problems, are doubly exponential time. They usually use Grobner basis. Even getting them to exponential time is non-trivial. And so this kind of work leads to new algorithms, and maybe they'll expand and generalize. Thank you.
We have time for a few questions, which you can ask at the microphones in the aisles. Okay, if not, then you can ask Avi questions afterwards. Let's thank Avi again.